the finite quotients of buildings.
Yeah, can you hear me?
Yeah.
Yeah. So I'm going to be talking about zeta functions of finite quotients of buildings. And coincidentally, this was the topic of the first talk I attended on my first visit to the Hebrew University that happened in this very room in a conference on expansion organized by Peter and Alex when I was a master's student in 2018. And that's when I first met Alex and Ori and so many others who are good friends today. It's been a great few years of my PhD here, and it's all thanks to Alex. And many better and more serious mathematicians in these talks have talked about Alex's mathematics and his contributions. All I'll add to it is it's rare to meet people as kind and as positive as him, and that really rubs off on all his students and all of us who interact with him. I'm very grateful for that. Alex, happy 70th birthday. Hope you have many more years of productive research. Thank you. Thanks for the invite, and sorry to wake you up at 9 a.m. It's really early. So I'll try to be elementary. It's going to be a relatively elementary talk compared to the other talks that we have seen. And the first, hopefully 20 minutes, I hope, not more than that, will be an overview of these objects, mainly so that you get some motivation, and at the very least, you get a feel for what objects they are, just lay them out, and maybe just get the notation right. So firstly, the zeta functions. Like when you want to talk about zeta functions of finite quotients of buildings, what are you trying to do? What's a zeta function? So in general, a zeta function is just a generating function which counts, can you see it? Is it big enough? Which counts the number of objects. I'll be vague and imprecise because the context changes and what you mean by it you can make it more precise even in generality, but number of objects of some weight assembled from some set of building blocks called primes. It's as general as this. For example, let's say you have one object A, which is, let's think of it as a prime, and it has weight 1. So I'm just going to have more A's, and what would be the generating functions of the number of objects of a weight k assembled from this A? It'll just be 1 plus t squared plus dot dot dot. This will be 1 by 1 minus t. So you're counting the number of multisets assembled from A, for instance. If A had weight k, this would be t to the k, t to the 2k. And if you had two such primes, then the number of multisets or objects assembled from this would just be, the generating function would be the product of both of them. Let's say this has weight k and this has weight L. This would be k into 1 minus 1 by t power L. So this is just a very general generating function, but it has a lot of nice properties, especially if the primes are something fundamental, and then you can start counting the number of objects. For instance, you can count the number of rational points, the number of points on a variety, or a lot of things. We'll see more concrete examples in our context, but some generalities. Let bk be the number of primes of weight k. Let ak be the number of objects of weight k. Then the zeta function will be A0 plus A1k, A1t plus A2t square plus dot dot dot. This is actually can be written in this way, as I just said, in terms of the product over the basic generating functions of this form. It will be like 1 by 1 minus t to the weight, let's just say n, times the number of objects of weight n. So this is called the Euler product formulation. So for those who came late, I'm just giving some very basic combinatorics of zeta functions so that we can then talk about what we are trying to do in the case of graphs and buildings. So this is the Euler product formulation. So you have the zeta function and you write it in terms of, so AIs are the number of multisets of weight n, and Bn is the number of primes of weight n. Another useful way, some sort of intermediary, is taking the logarithmic derivative. So you can actually write this as, let's say, exponent of something, where t bar k, where, so what I'm doing here is I'm just manipulating the zeta function a little to get another set of coefficients which will be a little more useful for us. Dot, 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 yeah. This is just a standard manipulation of a zeta function. Now, why did I choose this n's? Is because once you're given a zeta function as just a function, it's you can, once you get these n's, there's an easy way to get the bk's from it, because usually it's easier to have the zeta function as a function rather than knowing the number of primes of a particular weight. Because once you have this, then you can actually get an exact formula for, so this d divides k, so that you can take the Mobius inversion of this to actually find the number of primes of a weight k. And the Mobius function of k by d. So just to recap, zeta function encodes information about the weights of primes, and once you have the zeta function, you can actually compute the number of primes of a weight d just by taking the Mobius inversion of this series. Very broad generalities. Now, why did I talk about this? Firstly, nk, once you know nk, just by manipulating the zeta function, you can get the number of primes. But the other reason is we have some very abstract form of the Riemann hypothesis at this stage itself.
On the left bottom, I don't understand what's A and B. One of them left in the formula, one of them is not in the formula.
This one? So think of, so each of these is a prime of weight k. And an object is just a multiset of primes.
Okay.
So how many multisets of weight k exist? That is ak. So this is very broad generalities. You can adapt this idea in different contexts and get specific zeta functions. The broad idea is that you have these primes and you assemble objects out of those primes, and this gives you some correspondence between the assembled objects and the primes themselves. But this is just combinatorics.
1 over 1 minus t to the k.
Yes. I actually had it as 1 before and just added it. I forgot to add the k here.
Sorry, Bharat. I am a bit confused because with zeta functions I was expecting the variable to be in the exponent.
That's a good point. There's two kinds. That depends on the weights. So here, the weight of a multiset is the sum of the weights of the primes, in the way I've done it here. That's why you get a direct product. It's a convolution. It's like the degree of number of polynomials of degree k. So when you multiply them, the degree adds up, right? So in the additive setting, this is the way you do it. If you want to do it in the multiplicative setting, for instance, the Riemann zeta function, then the Euler product will have 1 by p to the s, because the weight of a product is actually the product of the weights in that setting. So there's a transformation between the two. It depends on the context you're using. In number theoretic context, you'll use the multiplicative weights. That's called the Dirichlet generating function. Over here, this is just a more basic generating function, which actually applies to a lot of contexts, as we'll see.
Combinatorialists have been using similar, the same thing, just with different names for a long time. They don't call it zeta functions.
Yeah, so
they call it, prefabs or some variant of the exponential formula. It's the same.
This is just a poset sort of analysis. It's there in many places, but people just go directly to the context instead of going through this. But it's a nice way to just keep in mind, especially when you want to generalize to an entirely new setting. So why I talked about NK is a very basic form of the Riemann hypothesis, which is something like, suppose this zeta function was a rational function. Just suppose, just to make life easier. Then this term can actually be written as something like f prime of t by f of t minus g prime of t by g of t. And when you actually, and suppose f of t were a polynomial of some form, let's say 1 minus alpha I alpha 1 t into 1 minus alpha 2 t dot 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 1 minus alpha n t, and g of t was another polynomial 1 minus beta 1 t 1 minus beta 2 t dot dot dot. Then just a very standard working out will give you that nk, just by comparing coefficients of the power series. Nk is actually the sum of the kth powers of all of these roots or poles, or beta nk minus alpha 1k plus alpha mk. So what's the point of this is that in different contexts, based on where the zeta function comes from, suppose if the zeta function is rational, usually there will be some trivial roots or poles that just come because of that context. For instance, if you take points on a curve, then you'll have 1 by 1 minus t into 1 minus qt, points on a curve over a finite field. So you'll have 1 and q over there. In other contexts, in graphs, for instance, as we'll see, you'll have the degree of the graph. There are many basic trivial sort of roots or poles that will occur in the zeta function. So nk will have that as the main term, and the Riemann hypothesis in some sense says that all the other terms of this zeta function's roots or poles are an order of magnitude smaller than that main term. For instance, in the Ramanujan graphs, that's how we'll see it. It's like the main eigenvalue would be p, which just occurs because of the degree of the graph, because of the finiteness. Then you want all the other eigenvalues to be square root of that. So those will occur as the remaining error terms. So this, in some sense, this is a way of, the Riemann hypothesis is a way of capturing the error term of nk and therefore the number of primes. This is, of course, in the classical theory, this is much more well developed, but this is a basic rudimentary form of the Riemann hypothesis. Okay, so we have seen just a vague picture of what the zeta function is supposed to be for. Now, I just want to mention one additional zeta function. I don't know much about it, but it's just to motivate the graph zeta function, which is the Selbach zeta. it's just to highlight that what you choose as primes is something in your control. Probably Peter can offer more insights on that. But so let's say you have H, which is PSL2.
Selberg once said that there should be an agreement among people that there are too many zeta functions. There should be a limit to how many can be defined.
So let's have the hyperbolic plane, and gamma is a Fouchian group. Let's just assume it's co-compact for now, because it's just an example. So now you have the hyperbolic surface. Let's call this X. You can define a zeta function on this where your primes are prime geodesics. So your primes will be prime geodesics. So by prime geodesics, I just mean winding number 1. So what this captures in some sense is it corresponds to the equivalence classes of primitive hyperbolic elements of gamma. So in the hyperbolic plane, you're not going to have cycles. So when you wrap it around, it's because of these elements of gamma that you're going to get geodesics. So this, now you can introduce these as a geometric term and get a zeta function out of it. So prime geodesics are going to be your primes, and you can define zeta of gamma of S.
What's your weight?
Length.
Alright.
And weight is the length.
No reason it should be integral multiples of anything, right? Just weird numbers.
So gamma this is just a formal way it's defined. I don't have too much of an insight on the exact thing. But what I want to say is that in the Selberg zeta, you see a new way of defining your primes, which is using geodesics. You define the zeta function. And the roots and poles of this zeta function are related to the spectrum of the Laplacian. And that's the trace formula. And so, in a sense, this is again related to the Selberg's theorem because of the connection between the zeta function and the spectrum of the Laplacian. And this is a theme that we'll see next in the case of graphs, which is you can, over here you define the zeta function as prime geodesics. Now you can ask the same question in the p-adic setting. And that's going to be a graph zeta function or the Ihara zeta function. And that's the starting point of what we are trying to do. So in the p-adic analog, let's take PGL, let's say QP, and its maximal compact subgroup PGL to ZP, which is a tree. And now again, you can you can take the orbits of gamma, co-compact subgroup, and now I'm going to say the primes are the analog of a geodesic in this context, which is primitive, non-backtracking, cycle classes. What do I mean by primitive is just saying that a cycle has winding number 1. It shouldn't keep going across. Non-backtracking is that at no point should I backtrack. It's a very local condition. And cycle classes is just saying that it doesn't matter what your root is. It's just the whole cycle that you're referring to. So this is your analog of the geodesics in this context. And so now you can define the zeta function of a graph. Z of t is P, this is the class of P up to the starting point, 1 by 1 minus t to the length of P. Okay. So now, as we saw before, we can do the same thing. We can talk about this nk business, which is x of sigma nk by k t par k. And in this case, nk will simply count the number of non-backtracking cycles of length k. Because as we saw, nk was d bd d to the k. So it's just taking all primes here, multiplying it by d so that you can probably loop around. So you get the number of non-backtracking cycles of length k. Now what's interesting here is that this nk in this case actually arises as a trace of a particular matrix. Trace of, let's call it L to the k, where L is an edge matrix, a directed edge matrix called the Hashimoto matrix, which takes a directed edge EI and EJ, and this is 1 if EI feeds into EJ and EJ is not EI inverse. It'll be more clear if you just draw a picture. So you have directed edges on both sides. L takes this edge, this directed edge, and takes it to all of those edges which feed out of it, except the backtracking. Right? So nk, the number of non-backtracking cycles, is simply the trace of this matrix power, which is nice because this immediately tells us what the zeta function looks like. So there's this classical, I think, by Jacobi, if I'm right, which says that x of trace of L to the k, t k by k, is equal to x of minus of the trace of I minus LT, which is just 1 by trace of log of I minus LT. So this is just a very classical little lemma which says that trace of log is log of x, So the conclusion is more interesting here. So we define the zeta function abstractly just using the Euler product. But what this tells us through these observations, firstly that nk is just a trace of a matrix, is that this zeta function is rational. It's just a 1 by determinant of something. And what is this L? This L, you can also give it a more algebraic interpretation. For instance, on the tree, I'll just draw a diagram and it'll be easier to picture. So let's take the tree. P10, P dot 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 1, 0, 0, P. So what does this L tell you? L says that you take, let's say, this edge and you take it to all of these edges. That's what L does. So this is actually, and you can describe this algebraically using fixing this edge. There's this subgroup called I, which is the Iwahori subgroup. So what I'm talking about is, okay, so what are the vertices here? Vertices are G mod K. So when I say I want to fix this edge, I mean I'm going to fix this, which means this is fixed by K. And I'm also going to fix this. This is fixed by 1, 0, 0, P, inverse, the conjugate of K. So I is the intersection of both of these, which will fix this. So now the directed edges of this tree are all given by G mod I.
Could you not write in the
Okay, sorry. So just like the vertices of the tree are G mod K, the directed edges of this tree are in correspondence with G mod I. And now when I want to talk about this operator L, what I'm saying is, okay, take a group element which takes this to this edge to this, and then just apply I on it, and you will average it all over these edges. So it's like an element of something like I, A, I, where A is one of the matrix which takes this to this, for instance. So this is a well-defined algebraic operation, this L. In fact, this is why we can hope to sort of generalize what we are doing over here in the graph case. Because in the graph case, it looks very combinatorial, like non-backtracking walks. But what it actually means on the tree, it corresponds to a certain subgroup which fixes edges and the double cosets of that subgroup. So L is an operator in, let's say, C, G mod I, if you are comfortable with this sort of way of doing it. Okay. So far what we have seen, we have defined the graph zeta function using the non-backtracking operator, and also given it some sort of an algebraic interpretation. Now let's go to buildings. A very rough and quick review, because I can't hope to cover much of it. Just to remind you of what the PGL3 building looks like. So I'm going to start with PGL3, QP, mod PGL3, ZP. So the vertices are this, G mod K, and each of them is of something like N1, P to the M2, P to the M3, something, B1, B2, B3, blah, blah. So you can define a color. So it's like M1 plus M2 plus M3 mod 3. And the links. So what does each vertex see? Each vertex just sees a flag. So it's like V1, V2, FP, Q. If you've seen a building before, good. If you haven't, just bear with me, because all we'll need is some algebraic structure to define what we could hope for as a zeta function. So what does the building look like? The apartments look like it's just a sort of triangulation of the plane. And if you have a vertex here, I have two sorts of edges. So you have, this is a vertex of color 1, 0, then this is of color 1, this is of color 2, this is of color 1, color 2, color 1, color 2. And then this is the apartment, so you'll have a lot more edges going to other apartments. This is probably all you can do right now in the short time we have. But if you know buildings, okay, let's try to define a zeta function for a building. What can you do as you did for graphs? You can again talk about some sort of gallery walks, some non-backtracking walks on edges a non-backtracking walk along triangles, just keep walking along the gallery. You can do either of them. Let's do both of them. So you have the chamber walk.
I think you need to change.
Chamber walk. Can you see this?
Yeah.
Okay. So how can you do a chamber walk? Let's do it blindly following what we did for the graph. I'm just going to define it as 1 by determinant of I minus LB T. I'll say what LB is. LB is the operator, just like the Ivahori operator for graphs, but now with the Ivahori operator for the building. So what it does to a triangle is, you have a triangle like this. It's a marked triangle with a root. It goes like this. I'm just going to take this triangle and it's all the other eyes. So on the apartment, it's like if I start with this triangle, I'm going to go to this triangle, I'm going to go to this triangle, I'm going to go to this triangle, keep going like this. So this is a walk, a chamber, sort of gallery non-backtracking walk. So this is one.
Or inside one apartment?
No, it's not inside one apartment. It's actually, you take this triangle, this corresponds to G mod I, the Ivahori. So you do it all over I. So you go across all the apartments. Just like in the graph case, it's not just linear, right? So this is the chamber zeta function. You can also define an edge zeta function. Let's call it E. The same way, determinant of I minus L1 or LET. What would this do? This takes this edge, let's say 0, 1, 2, this edge, and just keeps going across like this. This would, when you take modulo gamma, this would again curl back and form a geodesic. This is just like in the graph case. So you have another non-backtracking walk and a zeta function for that. So what can you do? Which is the right notion of the zeta function? Well, in the graph case, what's the interesting thing is,
Sorry, the edge walk doesn't change direction at all.
no, it starts like this, and on the apartment, it just keeps going.
No, but I mean, the angle doesn't change.
So,
It stays parallel.
yeah. But it goes across apartments, just like on the tree.
Yeah.
Okay, this is probably too fast, but if this is a good way of picturing it, but if you want it algebraically, it's even easier to do. Just take the parahoric subgroup that fixes an edge and then just move it across.
But sorry, in tree, any walk, non-rotating walk, is an apartment, or contained in an apartment.
Yeah. This is also it's contained in an apartment. So what's nice about the graph zeta, just like in the Selberg zeta, as I said, is that the Selberg zeta functions, roots and poles are related to the spectrum of the Laplacian. Similarly, the graph zeta is actually related to the spectrum of the adjacency matrix, which is the analog of the Laplacian over here. E minus V, determinant of I minus AT plus, did I use P or Q? I'll just use Q from now on.
Which Z is this? Curiosity.
This is the graph. The classical,
No,
just I minus LT. So what you see is the zeta function defined as geodesics. The roots or poles of that are related to the eigenvalues of the adjacency matrix. In fact, the Ramanujan property here is essentially the Riemann hypothesis for this zeta function. Ramanujan graph is the Riemann hypothesis. just by writing out 1 minus lambda t plus qt squared, just write out the quadratic formula and you'll see that this is what you think of as the Riemann hypothesis over here. So do we have something like that for the PGL3 walks? Will the Ramanujan property of higher dimensional complexes be seen in the zeta function of those complexes? Yes. Again, the same Selberg idea that it comes down to the information at the level of vertices and adjacencies. And that is the zeta function for finite quotients of buildings that I hope to spend the rest of this talk on. This is the formula that we are interested in. This is just the Euler characteristic, like E minus V, this is like triangle minus edges plus vertices. Determinant of I minus LE T, determinant of I minus LE transpose T square by, can you see? Or
Move the log to the left.
determinant of I minus A1T plus Q A2T square minus Q cube T cube I. This is the analog of this zeta identity for PGL3 buildings. And as it turns out, this was a result of Kang and Li from, I think, 12, and Kang, Li, Wang. Which year was this? I think 14. And as it turns out, the Ramanujan property for simplicial complexes is reflected here, because you see that the roots and poles of either of these.
Wait, what are we counting here? What's the other side of these?
This one?
Determinant.
This one?
That's a determinant. That's a determinant identity. What's the count in terms of closed cycles or closed?
Well, you want to, so the count is either 1 by determinant of I plus LBT, or you can use 1 by determinant of I minus L1T, or any of them. Those actually give you actual counts of some paths. This is a relation between the roots or poles of all of them, and reduced to something that comes at the level of adjacencies.
Yeah, but I'm trying to. So you had ZB and ZE.
Yeah. Yes, but I mean, this is a relation between both of those expressions. So this is ZB inverse, and this is ZE inverse, and this is another.
All right. So suppose I were to ask you what the prime number theorem is. I mean, these things are usually, you count them, so you'll be counting closed Barr chamber. By the way, over R, we don't know how to do this. The analog of the Selberg zeta function in higher rank. Nobody knows how to do it if the rank's bigger than 2, only if you have regulators which are one-dimensional. So it's very interesting that you can do it yet, which is why I want to know what you're counting.
So each operator will give you a different count.
No, are you going backwards here? I'm asking what you're counting.
Yeah, no. So I'm saying you have the LB operator. That's a zeta function for walking on
Galleries.
galleries, or so you're counting walks of a triangle. You have the LE and transpose, so now you're counting, it's a non-backtracking on the edges.
So when you count the gallery one, what are the volumes you count? Is it the co-volumes? How's it weighted? In other words, there it was the length of the closed geodesic for the conjugacy class and bring it into. If you go to higher rank in the real, I'm just saying this has been a major problem. Nobody knows how to do it.
What you can get here very easily is something similar to the IRR. Modification of this gives you, if you count in certain direction, fix the direction, end up in an apartment which is not parallel to any
So is it
particular
like a
thing.
systole? It's It's like a system.
Yeah, but it's not a system called the minimum. If you fix it in direction, unlike in the real case, if you fix it in rational direction, it's always closed. And count them, and then you get this rational C. To count the area, I don't think is C.
Yeah,
Maybe
so
they-
can you order them by volume?
But volume is complicated.
Because that's my favorite regulator problem. It's all about the class done. Yeah, okay, well, you're not going to write down what you count.
Not anymore. So, to continue, where was I? Yeah. So, the goal is to prove this, and this has been proved. So, this is the work of Kang-Li and Kang-Li-Wang, and it's a tour de force of representation theory and counting hyperbolic geodesics. But as it turns out, there's a much simpler proof of this, and this is what I hope to at least sketch in the next 20 minutes. And to motivate that proof, so the way Kang-Li do it is they actually take all the representations that occur in L2 of G mod gamma, and then look for k-fixed representations, Ihori-fixed representations, and just list it out. But this is a combinatorial relation between operators at different dimensions. And in the graph case, it's even more explicit and easy to do. And I'll show you a two-line proof of the graph zeta function, and then sketch a proof of how you can try to do the same thing over here. So in the graph case, you have L, which works at the level of directed edges, and A. So let's, okay. You have A and L. So you have edges and vertices. Let's take two sort of relating operators. So take an directed edge and let S be the starting point of the directed edge, and let T be the ending point of the directed edge. And so you also have its adjoints S star and T star going back up. So what is A? A is just going to be T S star, right? You start with a vertex, you take S star, so you take all of the directed edges going out of it, and go to T, you go to all of these vertices, and that is exactly A. What is L? L is T S star minus a sort of flip. So let's look at this. You have an edge, right? When you go to T, you go here. When you go S star, you go to all of these, including this. And this is the one you want to avoid, and that is going to be a rho. Rho is just an involution which reverses the edges.
Edges, you mean directed edges here?
Yeah, yeah. So L is a directed edge operator.
So the S and the T just send you to the source and the target.
Exactly. That's the reason it's S and T. So now just look at determinant of I minus LT. This is just going to be determinant of I minus S star T plus rho T. This is going to be, let's just put this in front just for simplicity, because now what I'm going to do is pull this out. This is going to be determinant of 1 plus rho T times determinant of 1 minus T times 1 plus rho T inverse times S star T. This is I think this is called the Schur complement, or it's a very useful and easy relation, which just says something like determinant of x plus yz is determinant of x times determinant of I plus z x inverse y. You can just write out this and prove it just using very basic, just block multiplication, or even easier, as Francois was suggesting. The point is that what you have done here by removing this 1 plus rho T outside is, here it was S star T, which was at the level of directed edges. But now you have T times something times S star. So now this becomes at the level of vertices. So if you write this out, what is 1 plus rho t? Rho was just rho square is I. So 1 plus rho t's inverse is just going to be 1 minus rho t by 1 minus t square, right? Because it's just a flip. Which means that this, this is just, what is the determinant of 1 plus rho t square? It's just going to be 1 minus t square times power number of edges, because you know that what rho is, it's just a flip. So it's just 1 minus t square times determinant of 1 minus t square minus t into 1 minus rho t by 1 minus t square times s star t, which is almost immediately determinant of 1 minus t square minus t s star t plus t rho s star t square. And you have another 1 minus t square in the denominator. It's a vertex level operator, so you can bring it out. Now what is this? This is just A, and this is just q plus 1. So you immediately get the formula. All you have done is just manipulate the matrix to go from the edge level down to the vertex level, just by flipping the order of multiplication. There's nothing to do with algebra of the tree or the representations or anything here. So what stops us from doing that for this? And that's, I hope I have the time to, sorry. I'll just give you a brief description of doing the same thing for this one, except that over here, so what, exactly. The message here is that the information is already contained at the adjacency matrix level, except that there's some memory of the walk. You just have to take care of this backtracking. It's just one step memory. So similarly in the building, it's similar except that you have to keep memory of the link. So here, let's see, you have, again, you have triangles or chambers, you have edges, and you have vertices. So now I'm going to have another row here, which will be rho cube is identity. So it just rotates the triangles. And I'm again going to have S and T. So this is S star T star and S and T. And I'm also going to have some intermediate operators between triangles and edges. Let's say you take a triangle and take the first edge of it, call it F. And this will be G. Then what are the operators that we are interested in? A1 is just going to be T S star as before. And now you have two adjacency operators corresponding to the two colors in the building. So it will be T S star and S T star. L1 is going to be S star T minus G F star. So what this says is you start with an edge, and L1 actually goes to all edges that don't form triangles with this edge. This is not allowed. You only go out of the link. So this is all possible edges going out of that terminal vertex. These are all edges that curl back into a triangle. So you take all of this minus this. And similarly, this is LE. And LB is, you start with a triangle, you take the second edge of that triangle and take all triangles that have it as the first edge. So that's what you mean here. You start with this triangle, take the second edge and take all triangles which have that as the first edge. That will include the rotation of the triangle also, if you just do this. So now you do this.
Why are there just two boundary maps?
The triangle.
You can recover everything else using these and rho. You can rotate it and then apply it again. So you will have a whole list of very elementary manipulations of these to get all possible ways you travel around the building.
First and second is in terms of the colors.
Hmm?
First is determined by the color, by the colors of the.
Which one?
You said first in G, but
Yeah, so we think of a triangle as a directed set of edges. So this edge, 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 and this is a root. So when I say G of this triangle, I'll just take this edge, triangle to edge. F of this edge triangle is just this edge.
No, it's a open pointed triangle. Like Hashimoto, you need directed edges.
so L triangle, yeah.
Right? The triangle comes with
With 6 or 3.
3. But 6 will be okay.
Yeah, so let's at least sketch what we can do next. So now you have determinant of I plus LBT. Do the same thing as we did earlier. You have a nice form over here. This is just going to be determinant of I minus rho t plus f star g t. So pull this out. So this is at the level of triangle. Now I can get everything to the level of edges by just pulling this out. So this will be like 1 minus t cube when you pull this out times to the power triangle. When you simplify it, it will be something like 1 plus g f star t plus g rho f star t square plus qt cube. This, what do you do after this? So this, you've brought it down to the level of edges just by the simple relation here. But once you reach here, it's a mix of vertex to edge and triangle to edge. So keep this aside. Let's just call this k of t. And let's look at determinant of I minus L1t and determinant of I minus L2, let's call it E and E transpose t square. When you multiply this out, you'll get something like, you'll still get this term if you have to trust me on this because it's just standard working out. Just multiply these expressions here.
Okay, we can believe you for this manipulation, but my question is, you said something but not explicit, so you claim also that if the complex is Ramanujan, if and only if Riemann hypothesis, but what is exactly Riemann hypothesis? What do you call your hypothesis? First question. Second question, what about higher dimension? Because in dimension 2, there is this quite a lot of symmetry. Things start to go to be very non-uniform on the link when you go up.
So you can develop a same sort of connecting expressions in all dimensions, but it just gets more clumsy as you go along, and we are still in the process of working that out. But at least in dimension 2, the PGL3 buildings, it's just one extra step from the simple proof that we saw. And regarding your question about Ramanujan complexes, what the Riemann hypothesis here says is that all the non-trivial zeros of the this I minus A1t plus QA2t square minus Q cube t cube, all the non-trivial zeros of this have absolute value 1 by q. This is, so in the graph case you had 1 by square root of q for determinant of I minus at plus qt square. So here one dimension higher, it's all of absolute value 1 by q.
What will be the random 4, you already know?
I think it'll be 3 by 2, I think.
So, what's a bit surprising is Ramanujan in the higher rank situation is a saying there's not just one operator, and you somehow put these together to make it a function of one variable.
Yes.
Where somehow naturally not a function of one variable.
Yeah, so the classical definition is a simultaneous spectrum, right? Yeah, but so this sort of expression I have in all dimensions, and I don't have it written here, but I know the exact polynomial here, even in higher dimensions. So that's enough to agree with the Ramanujan complex definition. But well, I'll come to that soon. I just want to tell you what happens next as quickly as possible because Devora has to talk after this. So what happens here is you start with the triangle level and you use these elementary manipulations to come down to the edge level, but you're stuck here because you don't know what to do next. But you still have this expression which occurred in the zeta identity. So let's play around with this, and you see that this can be written as kt plus something, and this something is actually some product of matrices of the form S star, T star, and Q into Q minus 1 T cube minus T square and ST. So, for instance, here you directly went to the vertex level, but over here you're going to go to a V plus V level, some intermediate level, because when you write this out, you don't get KT plus something just S star T or T S star or something simple. You get a sum of terms, which is why you allow for that and split it as 2V plus V instead of just 1V. And now you can remove this KT out of this and get something like, so this was determinant of this. And how much time do I have? Almost done. So this will be determinant of K of T times determinant of something like I plus R of T, some N K of T inverse M. So I reduce this to something at the level of V plus V. Instead of going from triangles to edges all the way to vertices in one step, because there's a sum of terms, I allow for the sum and just keep it as V plus V and get some expression like this. And it turns out that this actually simplifies pretty easily if you start, very explicitly start with an eigenfunction of the adjacency matrices, let's say lambda 1 and A2F of lambda 2F. Then you can sort of lift this F as S star of F, T star of F, and what's the other one? GF star S star of F. So S star of F is easy, you know what it is. T star of F, you know what it is. It's just giving that function value to those edges that either start or end at that vertex. What is this? This is, if you have a vertex, I give the function value to all those edges which are opposite to that vertex in a triangle. This is the additional degree of freedom that you have in PGL3, and which you have to take into account because this K of T is something at the level of triangles versus edges. So I don't have time to simplify this, but if you're interested, I can show you the full computations. But the point is this: all you need, the only information you need to simplify this is standard linear algebra manipulation. That's okay. Apart from the link structure, the link structure in the PGL3 building is a projective line versus plane graph. So in the graph case, you just for relating the spectrum of L versus adjacency, you needed that extra memory of where you started, what that edge was. Over here, that extra memory that you need is the projective plane graph, the link structure. So just using that link structure, you can go from this all the way to an exact expression using this F, and if you just write it out, the zeta identity follows instantly. So, I mean, it's a It's a much simpler proof than a 50-page proof using, p-adic representation theory of Castleman. And it's just plain matrix manipulation along with just using the projective structure of the link. That's the memory you use, and the rest is just observing very elementary matrix identities. What happens when you go S star T, what T star is.
I didn't get a clear answer. Does it going to work for higher dimensions?
This method, I haven't fully worked it out, but there are other methods we have partial results on.
Without the representation theory?
Yes.
Just pure probability.
Yes.
And what about other dimension to buildings? Like you take the symplectic proof?
I haven't tried that. So far we have results on higher PGL-N, and we have full PGL-3, and a lot of results on PGL-N. We are yet to look at symplectic buildings. Yes.
Christopher Fold used vertex simulation in the building of Dassault and TP to count normal subgroups of nilpotent groups. Have you seen this one? Because he uses very similar techniques and uses the chains of the homotopy clusters to compute zeta functions of nilpotent groups, and maybe the higher buildings will be of higher nilpotent.
I don't believe it will be. I mean, in fact, there is many years ago, I don't remember the details, I did some work with Marco Cassutori. We did the other way around. So we wanted to count some subgroups in important groups, and we reduced it to counting between.
Vertex enumeration.
This looks like a potentially much easier than all previous proofs, but I don't know.
Yeah.
I mean, the case of dimension 2 might be misleading because it's a bit more.
Yeah, she has to start.
So let's take the speaker.